Okay, well, good morning, everyone. Welcome to the last day of the first week of the summer school. Today we're going to talk about what I'm calling here medium scale optimization. And typically I would just call this optimization, this lecture. But I think that the focus of the summer school has been on big problems, and actually big problems. And the mathematical framework I'm going to talk about here is, of course, very general, but at least the algorithms I'm going to mention kind of briefly at the end, but sort of the style of setting up problems this way and solving them this way tend to apply to slightly smaller scale problems than we may be encountering here. So essentially, if you have something like problems with n variables, for example, then for the purposes of this lecture, we're maybe okay if the cost of the algorithm to find an exact solution is n squared, or maybe even n cubed. That would be kind of laughed at by the real big data folks, right? Because if you have a trillion examples or trillion variables, you can't have computational costs that scales like anything but order n, maybe order n log n. So, oops, I even left the old class number up there. That's too bad. So at least for the purposes of this course, of this lecture, I'm going to call this medium scale optimization. Though, as I say, this is typically just optimization. Okay, so let's what we're going to talk about today is a couple things. The first thing we're going to talk about is an introduction to what I'm calling mathematical programming, or just optimization. So you've seen a lot of this already in this course. I talked in my first lecture about machine learning problems as optimization problems. But here I wanted to define them a little bit more formally, and also define constrained optimization problems, which you've seen a little bit of so far, but the majority of problems that at least I talked about in machine learning were in fact unconstrained problems, at least in the form that I presented them. Though, as we'll see here, you can often transform them to constrained problems with some slightly different properties. Then I'll talk about some applications, and I'll be somewhat brief here because really the entirety of this summer school in some sense is about applications of optimization. And so you already know about some applications of optimization. Most machine learning problems can be cast like this, at least. So I'll mention a couple, but they're either going to be things you've already seen before, or maybe maybe one other example in there. And then I'll talk about two classes of optimization problems, spending much more time on the first one. So you may have heard this term thrown around so far, convex problems. Actually, who here you've all heard it before, I know, by now, because we've mentioned it a lot without ever defining it, possibly. But who here has a background in convex problems, has sort of seen what those mean? Okay, so maybe a third or so, at least a third that are going to raise their hands. So I'll define this more formally, because we've been kind of throwing this term out there, saying, oh, this problem's convex, or this one's non-convex. And I'll tell you what that actually means, and then tell you why that's a good thing for solving these problems. And then I'll talk very briefly about non-convex problems. So you've seen both of these, actually. So things like logistic regression or a support vector machine turn out to be examples of convex problems. And things like neural networks or deep learning typically tend to be non-convex problems. And so you've actually seen examples of both of these so far, but I'm going to cover this one in a little less detail this time because, to some extent, there isn't, well, it's a very, very rich topic here, but I'm only going to cover kind of the very, very basic methods. And then, finally, I'll spend some time on talking about how you actually solve these things. So again, we've already seen a little bit of how to solve them. For example, gradient descent or exact solutions for least squares were two examples of how you solve certain classes of optimization problems. It ends up that you can solve a huge range of these things, a very general set of at least convex problems, using existing libraries. And these are very powerful tools because at least for, again, medium-sized problems where maybe n squared or maybe n cubed cost is okay, there are libraries here that will solve these with very little effort on your part. And these are very good to know, not because you want to finally implement your algorithms this way necessarily, with the existing libraries. Sometimes you might want to do that. But these are really invaluable for checking, if your gradient descent method actually works. Are you finding the same solution as an exact method even for small problems, right? And so these even if every machine learning person will, of course, the paper is first about the problem and then about a better way of solving it than the off-the-shelf library. These libraries and tools are really, really important for developing machine learning algorithms and for kind of debugging things. So let's just jump right into mathematical programming problems. So I think that when I first presented machine learning, we'll say, I talked a lot about optimization, right? I talked about essentially the problems are all about minimizing this loss function. You minimize over your parameters theta, this loss function. And I think maybe, probably more than 15 years ago now, certainly, but maybe 20, 25 years ago, this actually was not necessarily how these things would be presented. There were a lot of different machine learning algorithms, and they would not all be presented as optimization problems. And so really, I should actually update this. Probably not 15 years, probably 25 years. But a big topic in the last 25 years in machine learning has really been about casting problems, casting machine learning problems as optimization problems, as the solution to an optimization problem. And that's kind of been one of the dominant, really, ways that we've started to attack problems now. Not the only one, of course, but it's a very, very prevalent one. And part of this is due to what I think is a pretty remarkable fact here. A lot of problems in machine learning, but I guess just in computer science in general, a lot of hard problems are sometimes cast in terms of sort of searching over discrete space. So, searching in a graph, finding the right path down a graph, building, the best data structure or something like that, building the best tree to capture certain data, stuff like this. And these are kind of fundamentally search over discrete structures, right? So there's a finite number of possible structures. It could be very, very big. In fact, it usually is very big. But there's a finite number of possible structures you have to consider. And they unfortunately end up being exponential time, a lot of algorithms to actually solve these. Or at least as far as we know, the best algorithms are in fact exponential time. Because you have to kind of search over all, in the worst case, all you can do is search over all the possible structures. So it's a very common kind of motif that comes up a lot when building algorithms to try to learn some sort of discrete structure. What's interesting is that mathematical programs seem harder initially because they are search over continuous variables. We want to find the parameters theta, where theta are a bunch of continuous variables, right? Your parameters they're real numbers. And so this kind of seems harder because now the number of possible solutions is infinite, right? And what's interesting about optimization and mathematical programming is that sometimes, certainly not always, and the same, by the way, goes for this too. There are certainly plenty of examples where you can find polynomial time solutions to discrete problems. But it seems like a lot of times in mathematical programming, a problem that we propose actually becomes easier if we let the variables vary smoothly in a range. And I'll show an example of that in a second, or later in this lecture when I talk about integer programming versus linear programming. Okay, so we've actually increased the number of possible solutions, yet our problem sometimes becomes easier. This is actually sort of a remarkable fact in some ways. I mean, it's actually not that remarkable when you think about it, but a lot of times making this sort of moving to the continuous space actually will make a problem easier rather than seemingly harder. So let's jump right in then and talk about optimization problems. I'm going to use a little bit different notation here than I've used in the machine learning lecture, which is really just because if you read books on this subject, you will find this notation, not necessarily the ones I use from machine learning. So for example, the variables we optimize over are usually called x, instead of x being the inputs for machine learning, here the variables are x. You have to get used to this. It's life. People from different fields use different notations, so it's actually helpful. You've probably already seen a lot of different notation, even amongst people all doing machine learning here. Some people use W for parameters, some people use theta. But here I'm going to use the more kind of optimization-based notation. So the basic optimization problem, and I'll just write it again, it's on the slides, but the basic optimization problem is written like this. We want to minimize over x some function f of x, And that's what we've seen before, basically, right? We've seen, we minimize the sum of losses on the examples over the variables, which in our case were the parameters theta. But then we're also going to add now some constraints. So I'm going to write subject to the constraint that gi of x is less than or equal to 0. Some function gi is less than or equal to 0. And there are, say, m of these constraints. I equals 1 to m. Just some notation here. X here is called the optimization variable. F is called the objective function. And the g functions are called the constraints. And here they're inequality constraints. We could also add equality constraints here. I'm not showing it here just because this is actually a fully general form. Because if you have an equality constraint, you could just say that g is less than 0 and negative g is less than 0. So that would imply equality of g to 0. I'm also saying this is always less than or equal to 0, right? Because if it's actually less than or equal to some constant, say 2 or something like this, I could always just put that constant into the function g and always have this be less than or equal to 0. So just for a canonical form, it's kind of nice to have it like this. Some more notation. The feasible region, which I often will denote C, is just the set of all x's that are feasible, right? That satisfy all the constraints. And the problem of optimization is to find amongst all the points that are feasible that satisfy these constraints. These are kind of hard constraints. You cannot violate these. But amongst these things, find the point that minimizes this function f. Right? So there could be a lot of points that are in the feasible region. There could be just one point, in which case it doesn't matter what f of x is. You have to just suffer that much cost. Or there could be what were the cases I just said? I said there could be a lot of points, there could be 1 point, or there could be 0 points. In which case, this problem is called infeasible, and you can't actually solve it. There's no solution to it. And just a little bit of notation. I'm going to denote x star. So x star here is a variable in Rn. F here is a function that takes variables in Rn as input, outputs a real value number. But x star we call an optimal solution if, first of all, x is feasible, it has to be feasible, and if for any other feasible solution, f of x star is less than or equal to x. So I mean, this is kind of very obvious, right? The optimal solution is the one that amongst the feasible points here minimizes that value. All right, so let me just talk about a little bit more notation now. You may see a lot of ways of sort of phrasing this. I'm going to try, for the most part, to refer to this thing here, this problem here, as a mathematical program. So it could be like and maybe special cases of this are things like linear programs or quadratic programs. It has nothing to do with actually programming. It's just mathematical notation. It's the same way that dynamic programming is called dynamic programming. This is called a mathematical program. But I'll usually actually just call it a mathematical optimization problem sometimes, or just really optimization problem. This is an optimization problem. And then optimization as a word, or mathematical optimization, or even numerical optimization, that's really about the overall study of solving those problems and ways of studying those problems and ways to solve them. Okay, so optimization is kind of the field, and that thing is an optimization problem, just to clarify that. And then finally, as I said before, this lecture here, I'm calling medium scale optimization. And typically, I would actually omit the medium scale part when I give this lecture, because typically this is what most people just cover in an optimization class. But because we're here talking about big data, I think I want to feel a need to emphasize that these things sometimes, the mathematical formulation, yes, that certainly is the case, but the algorithms that I'm going to talk about and the methods for solving I'm going to talk about often will not scale to the size of data we're talking about here. I mean, Alex before was talking about methods that are actually sub-ON, so it costs less than the number of parameters, less than the number of examples. And here we're way beyond that, right? We're actually n squared or even n cubed, or higher actually. Some of these things are really slow as far as what we've seen so far. But That's okay. I mean, for small scale stuff, we have 1,000 variables, maybe 1,000 constraints. These things actually work very well, and they're very, very robust, and they're very well studied. All right, so now a little bit sort of more division of this space. A common way to think about optimization problems is really dividing into two categories, and these are convex problems or non-convex problems. I should add, this graph here is not indicative of the size, the relative size of these problems. It might be indicative of the relative maybe number of papers that are published on these things, just because it's a lot easier to handle than those. But that's probably not even true there. There's actually a lot of work on the non-convex side too. I'm doing this like this just so in the next slide I can fit some more text into the right boxes here. But for the most part, and I'll cover this in some detail, and you'll see why this is the case in a second, but for the most part, convex problems, in some sense, are easy to solve. Or at least we have, again, this is very imprecise here, but for the most part, when problems are convex, that means we can solve them. And more importantly, we can not just solve them, we can find the exact optimal solution to this. So there is a global optimum, the best possible x out of all x's here. And usually, when we talk about convex problems, we're going to talk about things where we can solve that. On the non-convex side, and solve it in polynomial time. On the non-convex side, we usually can't. These are usually things where we can maybe find a local solution. We can still use methods like gradient descent to find good solutions, but there's typically no guarantee that we're actually finding the optimal solution out of all possible solutions. And we'll actually sort of prove why that is, why it's easy to find optimal solutions here and not here. Now, within each of these categories, there is a wide range of different sort of sub-categories that you may hear about. So things like semi-definite programming or semi-definite programs, quadratic programs, linear programs, these are all examples of specific forms of convex problems. And they're very useful forms of convex problems. And in fact, if you have heard of these before, who's heard of any of these before? By a show of hands? Okay, everyone. Or most people, because not everyone raised their hand, but maybe not everyone would raise their hand. Most of these things, if you care about it, these is actually, so linear programs are a subset of quadratic programs are a subset of semi-definite programs, etc. And there are many convex problems, I should say, that are not either of those two. But these are found to be very good representations of very broad sets of convex problems, to the point where a lot of our sort of practical work, when we think about convex problems, it is very often the case that we can formulate the problem, or at least approximately formulate the problem, as one of these. Maybe even going up to semi-definite programming, but they're sort of very, very powerful, these sets of tools here. On the non-convex side, there, of course, are a lot. You've already seen one. That's neural networks. Neural networks, the objective is not convex. Right? It has a composition of many different functions that together end up not letting you find the optimal solution. Another one that you may have heard about is something called integer programming. So the integer programming is like one of these kinds. So it's actually, people usually talk about it being like linear programming. But integer programming is like linear programming, though maybe also like quadratic programming. People just usually call that quadratic integer programming because for so long it was just linear. So these things are like linear programming, but they have additional constraints that the variables have to be integer valued. And that makes these things much harder to solve. So again, we're kind of going from this notion of discrete and continuous spaces here. These things are exactly the same as linear programs for the most part, or at least a version of them are exactly the same as linear programming, with the one additional constraint that we have fewer allowable solutions, and that makes them much harder to solve. And I'm not going to mention those other than just to find them. It turns out these are, in the worst case, exponentially hard to solve. So we're talking about really small problems now. But it's also the case that for some problems with the right structure, you actually can solve them reasonably well with certain kind of search algorithms. So even though they're in the worst case exponential, we can still sometimes do a good job. All right, so let's jump into some applications now. And in fact, this is going to be somewhat brief, at least in two of the cases, because you've already seen these before, and you've already probably been sick of seeing, another linear regression or support vector machine formulation. But it's worth seeing. So let's talk about some applications. So the first one I'm going to mention is least squares. And I'm not even going to bother writing it again, because you've seen this plenty of times before. But least squares is, we've seen it before, right? We have some input x. Now I'm going back, by the way, to the machine learning notation, switching very rapidly like that, you may notice. But doing that, you have some input x, some output y. Here I'm showing it in 2D just because it's easier to visualize that way. Our function approximator is this line x transpose theta, though I guess here I should probably include an extra dimension that allows for an intercept term as well. And our objective is to say, given these collection of x's and y's, we want to find the theta that optimizes this sum of squared errors. This is an optimization problem, of course, right? We have some function. This is our function f, in this case f of theta. And we're trying to find over all the possible thetas here, which one minimizes this. In this case, there are no constraints. There are no constraints here. So the GIs are all, there's m, I guess I'm using m here differently, but m in that formulation at least is 0 because there are no additional constraints. You could add constraints, by the way. If we knew for some reason that some of the coefficients, some of these parameters theta should be positive, say, right? We just knew that this was like a cost on something and you can't have negative cost. Then maybe we want to actually enforce that. Maybe we want to add the constraint that there's some theta I such that, I won't write it, but there's some theta I such that theta I is greater than 0. That would be a reasonable constraint to add. In fact, if you constrain them all to be greater than 0, this is a method called non-negative least squares, which is actually very common. It has a lot of applications because there are a lot of times where you really do want things you find to be non-negative. These are supposed to be like things that additively combine to give you the output, and you don't want negative combinations. So I should say positively combined to give you the output. Okay, so this is one example, and I won't dwell on it anymore because you've already seen it. This turns out to be convex, and we'll see why in a second. I haven't proven that yet, but it is convex, and we'll see why in a second. Here's another cool one. I really like this problem, actually. This is called a Weber point problem. So I have a bunch of points in r-dimensional space. Sorry, not r-dimensional, n-dimensional space, Rn. I call these xi's again. So you notice I'm again using the machine learning notation to have my variable. I'm optimizing over bz in this case, and my inputs be x. Somewhat intentionally, you have to sort of be used to that. I have a bunch of points in n-dimensional space, and I want to find the point z that minimizes the sum of distances to all of these other points, sum of Euclidean distances. And the distance here is defined as, I take all the individual coordinates squared, the difference in all of them squared, and I take the square root of that. And then I want to find the z that minimizes this term, the distance here. I can also write this whole term here. You may see the same distance written as, I could just as easily write that distance there like xi minus z 2 norm. That's just a distance function. And I want to find the z that minimizes all of those. Or the sum of them, rather. So how do you do this? So here's the question, actually. If n was one-dimensional, I have a bunch of points on a line. What's the solution? What is it? The average, I heard. Any other guesses? The median. So it is, in fact, the median. This is very easy to see, actually. I'll make it 5 just so it's obvious here. Well, I'll do this. The average and median, they look pretty similar. Let's put the one over here. Okay? So the average of these points would actually be somewhere here, right? Maybe like this. Would not be the same as the median. The median is this one right here. And it's pretty easy to see why this is actually the case. Because if you if your solution is anywhere to the right of this, well, you pay, so say I took this point here, right, and look at this point versus that point. In this case, I will decrease my cost by this distance and this distance, or decrease it by essentially, I have these two distances, so I will decrease my cost by 2 times that distance. And I will increase my costs by 3 times that distance, right? Because I pay more for this one, more for that one, and more for that one. So I actually sort of pay more 3 times. I get benefit times 2 and cost times 3. So the best thing to do there is to pick the point at the median. Now, this is important. If I were minimizing the sum of squared distances, that would be the average. The minimizing the sum of squared, if I had this term here inside instead of without the square, that would be the average. But when you don't have that square, it's the median in 1D. What is it in multiple dimensions? What's the analog of the median in multiple dimensions? And this really, so it's that. That's the only way to write this, right? There's no other way there's no closed form expression for this. And that really bugged me, actually. I remember I think that isn't quite right. You can find sort of algorithmic ways of approximating this, but there's no simple formula for this. Because the same median argument doesn't really work in multiple dimensions. Actually, what's the multidimensional analog of the median? It's not the point-wise median of each coordinate. It's something else. And this really bugged me. I remember the first time I was asked this problem, because there seemed like there was no solution, right? I think I was just in grade school or high school. I was asked this question, and it really frustrated me because I couldn't come up with an answer of what this point was. It was just this point. I didn't know about convex optimization then, so I couldn't actually give it even this solution. But it bugged me that there was no actual solution, seemingly. And what's interesting, though, is that this problem is also convex. So with standard off-the-shelf libraries, you can go ahead and just solve this problem and find the best point. And that's actually one of the best ways of doing this, because there's no obvious other closed form expression for it. Let's look at one more, which is a support vector machine. Again, we've already seen this before. The way I wrote it before was as this form, which you may have not seen, because it's not the way support vector machines are usually written. I'll talk about in a second how they are usually written. But essentially, it is the sum of a hinge loss term and a regularization term, which penalizes the sum of all the parameters squared, or this term here is also just equal to what's called the L2 norm of the parameters, L2 norm squared of the parameters. Now, if you've seen an SVM before, you probably actually haven't seen it in this form, because this form is not that common. People usually talk about it in terms of these geometric margins, stuff like this. The point I want to make now is a couple things. First of all, this is a convex problem. I'll show you in a second why it's convex, but it's also pretty easy to see just by sort of looking at these loss functions. Intuitively, you can prove pretty quickly this is in fact a convex problem. But this term here is kind of nasty because it's not differentiable. We can't. It has no right. It has no at 0, or sorry, at 1. The derivative is undefined. Right? It has this kind of kink in the function, so there's no derivative or no gradient there, and that makes it harder to find numerically exact solutions. So things like gradient methods still do work, and we sort of have been talking a lot about that, right? We just run gradient descent, and this case it's called subgradient descent, and that kind of works. But maybe more importantly, it won't, or at least it's very hard to do that and quickly, say, within a reasonable amount of time on your computer, to quickly find a solution that is exact to numerical precision. So numerical precision on a computer, say 10 to the negative 10. So we want to be within 10 to the negative 10. That's not really numerical precision, but that's, say with the error in the problem, et cetera, say 10 to the negative 10. It takes a long time to find a solution to that accuracy if you use something like gradient descent on this problem. Now, for a lot of machine learning, we don't care. We're fine with, say, 10 to the negative 2 error, probably fine. Relative error in our solution, that's probably fine. But if we really do care about finding the exact solution, this ends up being a pretty bad form for this problem. It's just really hard to find using that form. So what's done often instead is to transform this problem to a different form. And in fact, what's also done sometimes is just to write this problem in the other form to begin with, and use things like, call it things like a soft margin SVM and stuff like this. But I think this is actually the right way to interpret it. It's a loss plus a regularization. But if we want to solve this exactly, we need to transform this problem a little bit. And so let me show you how you do that. The idea here is that this term, that hinge loss term, is the one that's non-differentiable. So we want to get rid of that term by adding that term to the constraints of the problem instead of the objective. All right, so here's what we're going to do. We're going to take this term, this hinge loss term, which is the max of 0 and 1 minus yi xi transpose theta. And we're going to introduce a new variable, which I'll call psi I. I'm really bad at writing these, so I'll just make a little squiggle like that. I think I actually did one too many there. I think it's more like this. We're going to introduce a new variable, psi I, which is always going to be less than this thing. Sorry, greater than this thing. This thing's always going to be less than that variable. And now, using some fairly simple sort of transformations and arguments here, we can actually write the problem like this. So now what we've done is we've introduced new constraints to the problem and put these new variables into the objective. So let's see why this works. The first thing to note is that if the max of these two things is always less than that, that is just equivalent to saying that, well, the first one is less than the right-hand side, and the second one's less than the right-hand side. Right? These two are equivalent. Because if it's bigger than both of them, it's bigger than the max of them. Okay? So that gives us my two constraints here. That condition there is equivalent to saying these two things are, these two constraints have to hold. And now what I've done is I've taken this term, which before was the hinge loss term in the objective, and I've replaced it with this constraint. Okay? So this thing is always bigger than hinge loss. And I'm minimizing this thing. And I'm arguing that that is equivalent to just minimizing hinge loss in the first place. Right? Because this thing has to always be at least as big as that. And in fact, at the optimal solution, it will be equal to that. Because otherwise, I could find a better solution that gave you strictly less objective and still satisfy these constraints. So in fact, what you'll see is at the solution, this term, psi i's there, are equal to hinge loss. That was kind of a quick argument, but hopefully that, going through it again, that you can make sense of that. And this is actually the form that you will usually see a support vector machine in. You may actually also see the intercept term added explicitly. So instead of theta, you have like theta or w plus b. So you actually add the constant term explicitly because you actually don't want to regularize that sometimes. You don't want to penalize the term as constant there. They also sometimes swap this around, like you might see this on the right side here and this on the other side. But it's exactly this form that you'll usually see. This is what's called a soft margin SVM. That's one way to think about it, certainly in terms of the geometric margin. But I think it's easier to think about it in terms of hinge loss. And this formulation here is just the constrained problem formulation of what I showed you before. So what's nice here is that now all these terms, the constraints and the objective, they all are differentiable. Okay, so their derivative is defined everywhere. And that's what will let us use these off-the-shelf tools to solve this to numerical precision for small examples, certainly, but for reasonably small examples, we can solve this in, I guess the time, of course, depends on how big the problem is, but for, say, 1,000 examples, 1,000 dimensions, we could solve this instantaneously. It would be, less than a second easily on a good machine. Okay, so those are some applications. And what it hopefully gives you a flavor of is that while certainly convex problems are very limited in their scope, not every problem is convex, not every problem we want to solve is convex, they are still quite powerful. And so it's actually very worthwhile studying this subfield of optimization relating to convex optimization. Any questions about this or about anything so far? I should have already stopped to ask that, but I know it's early in the morning. Any questions? Yeah.
Now we have a huge number of constraints, right? So
yep.
As many as we have to use them.
Absolutely. Yes. So this is why I'm calling this medium scale optimization, this problem, right? So not only constraints, but variables too, right? You have a variable for each example, psi I. So if your data was, 5-dimensional, but you have 10,000 points, now you have 10,000 variables here. It turns out that you can do this intelligently so that at least for that one, your cost is still linear in the number of variables if you solve this in the right way. So it will be order m in your original problem, but order, I guess, n squared or something like that for where n is the dimension of your inputs. And you could do that sort of by doing it. By the way, the off-the-shelf default complexity is definitely not that. You have to use sort of sparse solutions to solve it and to have that be, in fact, order m. So already there is some mechanics involved, but any reasonable off-the-shelf solver will solve this in time that is actually linear in m. Those are actually optimizations you can just do ahead of time. There's no issue there. So yes, you certainly have a lot of constraints, but we're talking about small data, first of all, and second of all, solvers aren't as dumb as people make them out to be, actually, also. They have some good built-in stuff. So if you were to say solve this in Cplex, right? Cplex is a very common optimizer. It would pretty much be linear in the size of the data. By the way, yeah, question over there. With the which loss function? The min loss function? A new loss function, okay.
How do you check that it's convex or non-convex, apart from the definition?
Great. Okay, so the question, and I'm sorry, I didn't repeat the question before over there. The question before over there was about the complexity. Don't you have a lot of constraints you've added to this problem? This new question was, if you have a new loss function, how do you know it's convex or not? How do you know if neural networks are convex or not? That's a great question. That's what the whole next section's about, actually. So let me hold off on answering that one. Yeah. Uh-huh.
You take the second term and add it to the...
Yep.
That is, what is theta? So since you're already minimizing over theta, different theta, what is, let's say if I actually use that form, what am I going to use?
So, I mean, whether or not you put this on the right or the left, it's the same problem. And it's the same problem as this, too. Theta is the same thing here. We've added new variables as well. But the theta you get from this is the same as the theta you get from this. Theta is still the optimization variable you're minimizing over.
Is it not a preferable solution, preferable way to write it in the second way? Because if you do that, then you just have one constraint that psi I is greater than 1.
Sorry, so you're saying we can rewrite this to a different set of constraints such that...
You have psi I greater than 1. Right now, we have two different concepts of constraints. The psi I greater than 0 and psi I greater than 1 minus something.
Yep. I don't think so. The question was, can you rearrange this to eliminate one of these two constraints? No, you can't. So theta is a variable too, and this constraint compares theta and these two things, and you need both of them. Essentially this corresponds to the two terms in the hinge loss. You can't get rid of either one. No, so I mean, I'm not quite sure the way you're talking about, but no, you can't rearrange these to eliminate either variable. Unless you do it in terms of putting them back in the hinge loss, which sort of undoes what we just did.
I wasn't saying about eliminating a variable plus thing. Maybe I take it off.
Okay, yeah. But I think the question is that, no, in all practice, you cannot eliminate the constraints further than this to make it easier to solve. All right, so now let's talk about convex problems. All right, convex problems are, as I said, this subset of optimization problems that for some reason, and hopefully let's describe the reasons, or you'll have some sense of the reasons in a second, but somehow have become this sort of big dominant type of problem people think about in optimization. And I think it's this way because for a few reasons. First of all, a lot of problems that you actually do want to solve are convex. Including things like support vector machines. You want to solve them and they are convex. It's great. And, as I said, kind of roughly speaking before, but it's certainly true for these ones, when problems are convex, you can solve them efficiently. And I mean by efficiently, I mean in polynomial time. There are algorithms that will give you solutions that are exact to numerical precision and that give you the global solution, importantly, the best possible solution out of all possible ones in polynomial time. There's also a beautiful theory here. So if you look at the amount of papers published on the theory of support vector machines versus, say, the theory of neural networks, there are much more in the theory of these things because convex problems are really easy to analyze, relatively speaking. And there's really a beautiful theory about convexity, which we will not cover at all. Things like duality, these kind of topics, which I am completely omitting here entirely, if you've heard about duality before. It's this beautiful theory. It really is sort of a wonderful set of conditions that sort of tell you how you know when you solve these things and how optimal they are and how you could prove that something has no solution at all. How can you prove that a problem is actually infeasible? Is really a sort of a wonderful set of theoretical results there. And there really are lots of applications. Machine learning has been kind of inundated with applications for things like this, for solutions to optimization problems. But, as I sort of said at the beginning, be careful too, because a lot of problems we'd really like to solve are definitely not convex. Starting, by the way, maybe, with minimizing error in classification, minimizing 0-1 loss, right? Remember back when I sort of defined this loss function as kind of an approximation to this thing we actually want to optimize, which is just the number of errors it makes? That one we can't solve. You can't find a linear classifier that makes the smallest amount of errors. You can, but it's NP hard in the worst case. And the last thing I would say is that this is a fairly mature technology at this point. Meaning, I can download a piece of software that will just give me solutions to problems, and I can even write them in an incredibly intuitive way. And I'll show you at least a preview of that at the very end. And I would really encourage you all to check out some of these tools because they really make this whole sort of set of problems here, which at one point was pretty hard. At one point, casting these things as quadratic programs or linear programs in the right form to solve them was really hard to do. And so we had to be really sort of, it wasn't that hard, but it required some knowledge of these things. And now it almost requires zero knowledge. If you have some basic understanding, you can download code that will solve these things for you, basically written exactly like that, without any real effort on your part. All the hard work has been done. Okay, so let's talk about convex problems now. So a convex problem, I realized before in my last lectures that actually you couldn't see oftentimes the text when it was hidden by the thing. So hopefully this will be a little better. It's not ideal, I know, but I'll try to write on the boards this way. Okay, so a convex problem is I'm defining it here in kind of the silliest way, but it's a problem minimize over x, f of x, subject to x being in some set C. I'll just simplify that. You usually would write it like this again, but I'll just call it x within some set C, where the function f is convex and the set C is convex. Okay, I didn't say it. I'm going to be clear. I haven't said nothing yet what that actually means. But if the objective is convex, is a convex function, and the constraint set is convex, this is a convex problem. Okay, now of course, I've just pushed this off. What do I mean by functions and constraints being convex? All right, so let's first talk about convex sets. So I said this set C, x being in this constraint set. This has to be a convex set. What do I mean by that? Well, let's define this now. A convex set, so a set C, I'll write this because this is sort of the important definition. C is convex. What this means is that if I have 2 points in this set, so say I have 2 points, x and y, that are both in C. If x and y are both in C, and I'm going to be clear here, like this thing is convex, this thing saying it's convex is equivalent to this next condition here, that if x and y are both in C, then I can take any what's called a convex combination of the two. What that is I take some variable theta, and I apologize here. Here I'm not using theta to mean a real valued number, and in fact a real valued number between 0 and 1. So now x's are variables and theta is just some number. Again, this is just the terminology people use, so you have to get used to it. Theta is no longer parameters. But if I take theta in between 0 and 1, inclusive here, it could be 0 or 1 too, though the endpoints are kind of trivial, then theta times x plus 1 minus theta times y is also in C. What this term here is this term, if you can think of x and y as being 2 points, so this is point x and this is point y, this term here is just the line between the two. And importantly, not going any further out, but just between the two, right? Because if you pick theta equal to 0, that would be the point y. If you pick theta equal to 1, that would be the point x. And by interpolating theta between 0 and 1, you form the whole line between them, right? You're averaging them together. This whole thing here is called a convex combination of x and c. Sorry, x and y. And all that a convex set says is that if x and y are both in C, then any convex combination is also in C. So for example, this set here would be convex, because you pick any 2 points here, and the entire line connecting them is all within that set. This set here is not convex, right? Because I can pick 2 points that are both in that set, yet the line connecting them is not within that set. So that's the definition. That's all a convex set is. But that concept is actually incredibly powerful. So let's see a few examples. First of all, some trivial ones. All of Rn, right? That's convex. Take 2 numbers in Rn, take any combination, any line between them, it'll still be an Rn. Not going to somehow jump out of Rn. Intervals. If this is x1 and x2, if I have something like this, that would be a convex set. Right? That's a set of intervals to describe this region here. It's a convex set, right? Because any 2 points in it, the line connecting them would also be in it. I'll actually prove a slight generalization of this in this next slide. In fact, you can generalize just intervals to any set of linear inequalities. So if I have the set of all x such that ax is less or equal to b, where A here is a matrix. So X is an Rn, A is an R to the m by n. It's an m by n matrix, and B is in Rm. So these are essentially a set of m linear inequalities, this set here is convex. And the way you prove that's pretty straightforward, actually. All you should do is say, well, if I take 2 points that both satisfy this, then I know I have ax less than or equal to b, and ay is less than or equal to b. Oops. Okay, so I have those two things. I can add them up. Right? Well, actually, first of all, let me scale them, right? So this will also imply, of course, that I can just scale these. I can scale this one by 1 minus theta. Okay, no problem there, right? Theta, remember, importantly, theta is positive. It's between 0 and 1. Therefore, also, or non-negative, I should say. Therefore, also 1 minus theta is also non-negative. So both these two things still hold. Very important here that theta has to be between 0 and 1, or this would not be true. Right? Because when you multiply by a negative number, you can flip the sign of the inequality. Or do flip the sign of the inequality. Now let's add them up, right? So now we just add these two terms. And so because this is less than that and this is less than that, we know that theta times ax plus 1 minus theta ay is less than or equal to theta b plus 1 minus theta b. Okay, and just rearranging terms now here, just moving in, taking the a out here and distributing things. This is just going to be a times theta x plus 1 minus theta y less than or equal to b. Therefore, this term here is also in C, right? It also obeys those linear inequalities, and so we're done. Any questions about that? Okay, great. So that's a pretty powerful concept, actually. Any set of linear inequalities is a convex set. Doesn't matter the coefficients on A, coefficients on B. They're always a set of linear. They're always convex. Linear equalities. The proof is exactly the same. If ax equals b, then this notation here, just replacing all the inequalities with equalities, always holds. In fact, that would even hold for these not being between 0 and 1, but don't worry about that. For between 0 and 1, it certainly holds. The proof is exactly the same, in fact. The intersection of convex sets is also convex. This is actually a really important one, because oftentimes we define our feasible set as the combination of many different sets of convex constraints. So it has to satisfy all these things. This one's also fairly intuitive, right? Because if x and y are in all of them, then, well, the combination of x, these are all convex sets. The combination has to be in all of them, and therefore it's in the intersection of all of them. So that's sort of a 0.5 line proof, maybe, that this in fact holds. But it's very important. This, for example, would not hold for unions, right? You can have two convex sets. I mean, circles are both convex, right? So that's a convex set. That's a convex set. But their intersection is not convex. Or sorry, their union is not convex. The intersection is convex. It's empty. The union is not convex, though. All right. So that's all I'm going to say about convex sets. Now let's talk about convex functions. Convex functions are defined in a very similar way, actually. And the definition of a convex function is the following. Unfortunately, I can't. Oh, here's one. No, I have to put them both behind. I did the wrong order here. How do I want to do this? Okay, I'm going to have to just unfortunately hide this from view, because otherwise it will be hidden on the video forever. I know people here can see it, but I kind of want this to be visible, unlike my last lectures, unfortunately. Okay, so a convex function. So a function f is convex if for any two variables x and y. So f here is going to be a function Rn to R. Still All right, so f is from Rn to R. And if it's convex, if we take any two inputs, x and y, in Rn, and you can actually make very similar definitions just based upon functions that are only defined on subsets of Rn, but I'm just going to be simple here and define this function as mapping all of Rn to R. If we have sort of subsets that we want to allow, I'll just let us encode those with constraints rather than in the function itself. But actually, there are a few exceptions, like the log of a term is not defined from negative numbers, say. So there'll be a few cases where the domain of this is not all of Rn, but effectively the same thing applies just to numbers in the domain of the function. So if I have 2 points here, and I look at a convex combination of these points. So f of the line, really, of x of f of the convex of some convex combination between these two things. The definition of convexity says that this thing is less than or equal to theta times f of x plus 1 minus theta f of y. That's the definition. What this says graphically is if I have a function here, right, and I take 2 points, x and y, if I draw the line between them, okay, and that line between them is this term here, right, because I'm taking the average of these 2 function values, right, so that's this term here is the dotted line on my graph. This term here would be the solid line. If I take the line between those 2 points, that lies above the function itself. Okay, and that's what convexity is. It could lie on the function too. So like a linear function is also convex, but it has to be less than or equal to that. So this function would be convex, assuming it goes on forever, or this is the whole domain. This function would be convex too, assuming I can draw a perfectly straight line there. Because the average of these 2 points is still less than or equal to, in this case it's equal to the line. But this function would not be convex, right? Because I can take 2 points here, and the average was not above the line, or the function itself. The line between these 2 points does not lie above the function itself. And I mean, there could be regions where it does, but this whole function here would be non-convex, right? Because even though there are some places, for a function to be convex, it has to hold everywhere for any x and y. If negative x is convex, we say f is concave. And concave is also just as good, really, because we like concave functions too. By the way, there are a lot of functions that are neither convex nor concave, of course. For this function, for example, right? Neural networks are another one. But it's not like it's concave because it's not convex. It's neither convex or concave. And finally, f is what we call affine if it's both convex and concave. And that really just means it's on a line. There's really one case of function that is affine, and it's this one. It's a linear function. So to be specific, linear usually means there's no additional term here, whereas affine means there's an additional term here. So you can have a constant term when you're affine, because this term is still convex, right? You could add any constant term. I can shift this line up and down as much as I want. It'll still be convex. So this term here, this affine function, is in fact both convex and concave. And that's for any A or any B. Those can be positive or negative or whatever you want. All right, so that's the convex function. Let's think of some ways to test for this now. So I think this is sort of where we got to before. Come up with some new loss function. How do you know if it's convex or not? Well, now we have actually a definition, right? So you could just try to prove this directly and try to argue that for any 2 inputs, and say if our function is a loss function, and you would say for any two sets of parameters, the average between those 2 parameters is lower. The function evaluated the average of 2 parameters is lower than the average the average of 2 function values at each parameter individually. So you could just sort of prove this fact directly, and sometimes you can do that. That works sometimes. But But typically, that actually is, well, not typically, I should say. Sometimes, though, that's not the best way of doing it. There are actually sometimes better ways of arguing this. It can be actually kind of hard to prove directly this is the case. Though, of course, I mean, this next thing will directly imply that. So proving this is the same as proving that. But a more common condition you will see for people to verify convexity has to do with the second derivative, or the analog of the second derivative for vector input functions. So intuitively, you can think of convex functions as functions that kind of curve upwards, right? They're kind of bowl-shaped. They're always going more and more up. And they have to be. I mean, they can be flat too, but if they're curving, they have to sort of keep increasing their curvature more and more, because if they ever do anything like this, where they're sort of increasing, and even they still keep increasing maybe, but not enough to, the curvature stops increasing to a certain extent, then they're not convex anymore, because then you have something like this, right? So even though this function actually, if it goes on like this forever, is always increasing, has only one global optima, it's still not convex, because there's this region here where you can still draw a line between 2 points and it lies below the function. So functions to be convex, they have to kind of keep curving upward always. And in 1D calculus, that would be equivalent to saying that the second derivative of the function, not the first one, because the first derivative of this can be positive or negative, right? It's negative here and it's positive here. But the second derivative says, how does that first derivative keep changing? So say this is our function. This would be the, say this is f. Then f prime would be something like this. And then maybe f double prime would just be, where this is the 0 thing, because this function here is always increasing. And so the curvature of the function here is always increasing. So the constraint that it be convex for a scalar input says that the second derivative has to always be greater than or equal to 0. The analog of this for vector input functions, which is what we really care about, because we typically we want to optimize over a set of vectors inputs, not just one variable. The analog has to do with a quantity called the Hessian. So the Hessian of a function, which I'm going to write like this, and this should recall the notation of gradients. I'm just putting a 2 there, which is the second derivative. The Hessian of f, this term here is a matrix. Okay, so this is a matrix, which is n by n. And in fact, this whole thing's a matrix. And I'll just write it again. It's defined as the following. The ij element of the Hessian is just equal to the derivative with respect to xi, and again with respect to xj. So this is just equal to the partial derivative. And we're writing partials here again because the function depends on more things than just those two variables. But this is the partial derivative, which we'll write as partial squared, because we're taking two of these partial derivatives, and then the partial xi, partial xj. Okay? And that's just the definition of the Hessian. So it's actually very analogous to the gradient. Remember, the gradient was just sort of the gradient I term was just the partial derivative with respect to xi. This is just kind of, you can think of it as the gradient of the gradient, but that's actually not quite right, because gradients are only defined for functions, and the gradient is a vector. So kind of like the gradient of the gradient, though, if you kind of squint and forget about some of the technicalities. All right, so remember, the condition for convexity in the 1D case was that this second derivative had to be positive. Well, the analog here is saying that this Hessian, this matrix here, has to be what's called positive definite. And we're not going to describe what that means exactly. There's lots of ways of describing that, but the simplest way is just, well, I'm not going to get into too much detail about what it means exactly. But the simplest way, the definition of that just says that if I take any vector z, then for all z in Rn, z transpose times the Hessian times z, that has to be bigger than or equal to 0. That's the definition of positive definiteness. You have a matrix of positive definite if and only if you take any what's called a quadratic form with that matrix, you have something that's always positive or always non-negative. That's positive semi-definite. Positive definite is if that's always strictly greater than 0. Okay. Another way of defining positive definiteness, or an equivalent condition actually, is that, for those that know what this means, the eigenvalues of this matrix are always greater than or equal to 0. That's another way to verify positive definiteness. And there are other conditions too that you can use to define positive definiteness, but it's sort of like the analog of positivity for matrices in some way. So I should also say, if this is a scalar quantity, so if in fact the function is one-dimensional, that's exactly the same as if the second derivative is always bigger than 0, right? Because if this is just a scalar quantity, then this would just say that this would be z squared times this thing, times a, say. And for that to be bigger than or equal to 0, well, a has to be bigger than 0. Yeah?
So I guess it's easier to use this formula compared to the eigenvalue one, because this way we do not have to compute any eigenvalue.
Wait, sorry, this one as opposed to the eigenvalue formula? So the question was, is it easier to use this than the eigenvalue formula? This is equivalent to the eigenvalue formula, so this is actually exactly the same.
So when I'm testing for convex.
So it's often easier to use this one than the definition of convexity. This is the same as the eigenvalue formula, though. So the question is, like, what's easier? It's hard to say what's easier, right? Sometimes this is more immediate from the definition of the function. You can easily show that its Hessian is positive definite, whereas showing that directly seems harder. But it takes about 3 lines to get from this to that, so they're really the same. So if you can show this, you can show that. You don't even usually bother, because that equivalence is known. The eigenvalue, there's a question about eigenvalues too. If you can show the eigenvalues of this thing are always positive, that implies this immediately. And similarly, if you can show this, that immediately implies the eigenvalues are positive. So those are really equivalent. That's just sort of the definition of positive definiteness, or positive semi-definiteness. Yeah?
I think here the requirement is the function should be second-order differentiable.
Yes, so I'm assuming right now that all these functions, all these things exist that I write. So I'm kind of glossing over. And the same with the domain, by the way. It's only differentiable on its domain. The domain has to be a compact set, stuff like this too. I'm kind of ignoring all that. So actually no, it doesn't have to be a compact set necessarily to get back. But it has to be differentiable on its domain and things like this. So I'm ignoring some of the math there, but yes, they have to all exist. Yeah.
Can you go back to the definition of the convex?
Yeah.
So
Function or problem, you mean?
Convex problem.
Okay, convex problem. This one.
So I can also imagine a very simple example of non-convex functions when you restrict it to a constraint, it becomes a convex problem, right?
Yep. So the way you can do that is, right. So say we had this function here, right? And I put this as this thing. So if you can do that, you can always define another function f that is convex that for which this holds. Namely, I'm going to take this function, a new function, and define it as being equal to the old function on this range and infinity everywhere else. And that's a convex function. So for any time where you can write a problem, you can make f convex. Yeah. That's a great question. Sorry, I keep forgetting to repeat the question for the camera. The question was, can't we come up with a problem where f is only convex in a certain range, but it's non-convex in general? And yes, you can, but you could always just make a convex version of that same function. All right, so let's talk about a few examples now. And I won't spend too much time on these because it's actually pretty straightforward, most of them. The exponential function, that's convex, right? So let's see. How do I want to do this? Maybe I will push these all up. Oops, did I lose my, no, I have my eraser right here. Carrying it the whole time. All right, so some examples. So exponential. This is a 1D function, exponential of a to x. A can be any number. A does not have to be positive here. A can be negative too. That's a convex function in x. And it's really easy to show this. You can take the derivative twice. After the derivative twice equals a squared times the exponential of ax. This is always positive. That's always positive. Therefore, the product's always positive. Always, in this case, it's actually always negative. This could be 0, I guess. But combination's always non-negative. The product's always non-negative, so it's convex. Negative log, same thing. Take the derivative twice, it's convex. Euclidean distance squared. So f of x equals x transpose x. This is now for vectors. This one and the log were 1D functions. But if f of x equals x transpose x, the easiest way to prove this is to show that the Hessian here is the identity. And it will just pop out immediately, therefore, that the identity is always positive semi-definite. You can verify that. And so, in fact, this is a convex function. Norms. The 2 norm, for example, is also convex. So interestingly, if I take this function, take the square root, that's also convex. That one is not very obvious, I should add. That one, for example, is not differentiable, so the Hessian is not defined. So you can't use the Hessian condition to show that is positive, that is a convex function. The way you actually show that this is convex is through a property of norms called the triangle inequality. And that actually pretty immediately tells you this function is convex. But actually, in this case, you do just use this definition directly, because you can't use the derivatives at all, because those are not defined, or this function here is not differentiable. All right, so this is a convex function, but this one you cannot verify with the Hessian inequality, or Hessian positive semi-definiteness. Here's another really important case. This is more of a general rule. If you have a bunch of convex functions, fi, and you take a non-negative combination of these, so you take a sum of a lot of functions with some weights w that are all non-negative, so the weights have to be positive. Otherwise, I mean, they couldn't be negative, right? Because otherwise you could just have negative f of x, and that would clearly not be convex. So as long as the weights are all positive here, any weighted sum is convex. And this is a really useful property. This, in fact, is exactly what we used before to show that loss functions, if a loss function is convex for a single example, it's convex for all the, for minimizing the loss function, minimizing the sum of losses over all the data points is also convex. Right? And that uses this property. And in that case, the weights were, say, all 1. And we're minimizing the sum of loss functions. And so that's convex. And what it turns out, one thing that kind of happens in practice is that oftentimes when you want to verify a function is convex, it can be easier to just appeal to these rules than it is to derive the Hessian, right? If you can show that, like, say, a loss function is convex for a single example, then you know the sum of loss functions is convex just from that. You don't have to prove it sort of every time from scratch. You can use these rules, and then, you get pretty far with those. And in fact, these kind of rules, this is being a simple one, are actually how a lot of these programs for solving convex problems actually work. All right, so a couple more examples. Negative square root is convex. Here, I am restricting the range of the function. I guess I did it for the log too. The log also, x has to be greater than or equal to 0. These are all compact domains, therefore. Here again, for the square root, we don't want to talk about complex numbers here, so we're just talking about the square root being a real quantity. Therefore, we have to constrain x to be positive or non-negative. But in non-negative, the square root looks like this, right? So the square root the negative square root looks like this. And that function, this function here doesn't come back up. Sorry, keeps going. That function is convex. Log sum exponential, for those that are interested in this. That's another actually kind of curious one. That one's, you have to just take the Hessian and show that. Basically, if you take the exponential of each term in x, add up those exponentials, then take the log, that's convex. That one isn't that easy to show. That one requires the Hessian usually. That's at least the simplest way of doing it. The maximum of convex functions is also convex. This is a really very, very cool one. So if I have a bunch of functions, so say I have a bunch of linear functions. We know linear functions are all convex. A bunch of linear functions. And look at their maximum. Whichever one, these are all defined over everything. Look at their maximum. So that would be this function here. That's convex. In fact, that was one way to show that the hinge loss is convex, because each term inside that max is convex. 0 is a convex function. It's just a pretty boring one, but it's convex. So is the other term. The other term was linear, actually, in theta. And so therefore, it was affine in theta. And so therefore, the max of the two is convex. So I can actually show the hinge loss was convex, even though it's not differentiable. Remember, it's not differentiable at 0 or 1, just by appealing to these rules. And so we can also combine functions. So for example, and there's more rules than just this, but a simple one would say, for example, that f of y is convex in y, then f of some affine function of x is, or really a whole matrix times x, so several affine functions of x. This is also convex in x then. So you can compose a linear function inside a convex function, and the result is still convex. This would be one way to also show that, say, least squares was convex, because what we had was you had a square, which is a convex function, and you had affine functions inside of that, and therefore the whole thing is convex. You can also show it by appealing to the Hessian, but these things are all kind of one and the same. Okay, so and the last thing I'll say is another common convex set. Now, relating convex sets to convex functions, a common convex set is what's called the sublevel set of a convex function. So if I have some convex function, and I have some level, say alpha, I use C there. I guess I'll just use C. C. Then the set of all inputs, and it's important that I'm talking about the input line now, so I'm talking about this set here. The set of all inputs that are less than this value, that's a convex set. And that follows exactly from the definition, effectively, of a convex function and a convex set, that these two things this will imply that's a convex set. And in fact, because of that, it's more common to actually write convex problems this way. So remember, at the beginning, I wrote convex problems, or optimization problems, in terms of some functions being less than 0. And this kind of relates these two things, right? Because essentially, I can write, I had a form for my convex problem. I think I might have erased it by now. No, here it is. So this is my form for a convex function. Of course, you can't see this necessarily. Here's my convex function. I had this weird thing saying it has to be in C, where C is a convex set. Now, that can be hard to define right? So it's actually very common to define instead the convex set C as some set of functions all having to be less than or equal to 0, and maybe being equal to 0 too. In order for these things to be convex, G of I, those all have to be convex. That means their sublevel sets are convex. That means the intersection of all the sublevel sets is also convex. So this whole thing's convex. And H of I's have to be affine. To be equal to 0, they have to be, it has to be the case that H of X is less than or equal to 0, and negative H of X is less than or equal to 0. So the function has to be both concave and convex. Therefore, it has to be affine. I think that was kind of a long sentence there, but let me just repeat that. A equivalent way to write a convex problem is minimize f of x, where f of x is convex, subject to a bunch of GI terms, where the GIs are also convex, being less than or equal to 0, and hi terms are equal to 0, where the hi's are all affine. So the inequality constraints are convex functions. The equality constraints are affine functions. So I could write the hi as just, A transpose x equals B or something like that. But the important point here is that if any one of these functions is not convex, or if any one of the h's are not affine, this is not a convex problem. It only takes one to kind of ruin it, right? So they all have to be convex, the f and the g. The h's all have to be affine for this to be a convex problem. Now, one key property of optimization problems, and this is maybe the key property that makes them so useful, is the following. For convex problems, if you have a local solution, that means, and I'll define this in a second, because this is actually worth sort of proving in some detail. If you have a local solution, in other words, you have a point where all the points around, you have some point x where all the points around that point are greater than or equal, the objective of all feasible points around that point, I should say, are all worse or no better than the current point. So, here's a function, right? This here would be a local optima because all nearby points are bigger than it. But and this is not a convex function, clearly. The nice thing about convex functions and convex problems in general is that local optima are all global optima. This is really the key point, in fact. This is not the case, for example, in a neural network, which is why in a neural network, you know that just because you found some point with 0 gradient, that may not be a global optima. You could be in a really bad place still. For convex problems, that is not an issue. For convex problems, if you were at a local optima, if you found gun gradient descent and you're at a point with 0 gradient, say, for a smooth, unconstrained problem, that is a global solution. You don't have to worry about local optima. And this is actually very easy to show. So I want to just go through. I won't write it to get down again, but I want to at least go through the proof of this. This is kind of the key property, I think, of convex functions. So a point x is globally optimal if, first of all, x is feasible, and there's no y that's also feasible such that f of y less than f of x. Right? So it's the best of all feasible points. Now, and a little more, so I mentioned this before, but a little bit more formally, a point is locally optimal if it is feasible, and for all y within some radius of that point x. Okay, so for all y such that x minus y is less than some r. And that can be, r can be as small as you want, but there just has to exist some r such that this holds. If that is the case, then for all feasible y, we could say that there is no f of y such that f of y is less than or x, or equivalently, for all other y within that neighborhood, f of x is less than or equal to y. That means it is locally optimal. There's no point within this region R, within the radius R, that is better than f of x, but better than x. Okay, so these are the two definitions. And the proof of convexity, or the proof that convex optimization problems, for convex problems, all locally optimal points are also globally optimal, actually just follows directly from the definition of convexity. So maybe I'll go through it a little bit. Let's see, I think we have time. Okay, so I won't go through the actual sort of details of the math here, but what's going to happen is the following. So I'm going to pick some x that is a local optima. Okay? And I want to say, could there be a point y that is better than this? Could there be any point y that is better than this point? F of y is less than f of x. And the way I'm going to do this, we know this is a local optima, right? So we know that there is no y within some r. So we know there does not exist a y such that this holds, and f of y is less than f of x. But let's suppose there exists some y such that f of y is less than f of x. We know it can't be within this range. I should probably say something like y prime here. But suppose there exists something somewhere else. Okay? This is the proof by contradiction. What I'm going to argue is that this would imply that there is also a point within radius r that has lower objective than x, and that would contradict the local optimality of x. Okay, so that's the intuition. That's really all it is. And importantly, all these points, y and the new point I'm going to instruct, they're all also feasible. Okay? So it's actually very simple. I'm going to pick a point z, defined like this. Z is a convex combination of x and y, where theta is of this form. And a little bit of math will show a couple things. First of all, x minus z is less than r, so x is in the neighborhood of r. And if f is convex, then we know, in fact, f of z is less than f of x. All right, so that would contradict our assumption on the local optimality of x, and therefore we know, that this cannot be true. And if you want the details, really the details just come out from this particular choice of theta here. This choice is made such that we are, in fact, closer than r to x. And because of convexity, a couple things happen. First of all, z is also feasible, right? Because we assume that x and y are both feasible. The feasible region is a convex set. Therefore, we know that this combination is feasible. And we know also that this is actually less than this because convex combinations of, the function evaluated here has to be less than the function evaluated here and evaluated there. And so we're fine. And really, this is just the quick little proof here. It just shows that for this choice, we do have x minus z being less than or equal to r, and therefore it's feasible. It's closer than radius r to x, and it has to have objective less than x. So therefore, this couldn't be true. So, it's a very quick proof, but it's a really important one for practical reasons. It means that, again, as I said, every time we're at a local optima, we're also at a global optima. That's a very powerful criteria there. Okay, so we've sort of gone through a lot of problems here. And I want to just now return to sort of some examples, then I'll talk about how we go about actually solving these things, though there I'll be very, very high level about that. Okay, so now we sort of have definition of what a convex problem is. Let's talk about some examples. All right, so one example that you may see a lot is something called a quadratic program. Quadratic programs are written in the following way. We minimize over x this function here, x transpose q of x, where q is some positive semi-definite matrix, and R can be any vector, A can be any matrix, and R m by n. F is another matrix. So essentially, we're minimizing that function subject to some linear equalities and some linear inequalities. And we know the constraints here are convex because we proved before that linear inequalities were convex, right? Linear equalities are also convex. Therefore, the summation of both those things is a convex set. So we know that the feasible region here is convex. And it's actually fairly easy to show also that the objective is convex too. If you go through the math, what you'll find actually is that the Hessian of that quadratic term there, in fact, the Hessian of the whole thing, is just q. And we actually assumed that q was positive semi-definite. So therefore, the Hessian is positive semi-definite. And therefore, this function here is a convex function. Okay, so that's good. We have a set of problems that are in fact convex. Let's actually go back, and I probably should have put these later in the slides, but let's just, sorry, pardon me while I flip back. Because these are all also convex, these examples I gave before. So least squares is convex. You can sort of prove this in a few ways. First of all, there are no constraints we have to worry about here. So no constraints. It's just a objective. We just need to show this objective is convex. Couple ways you could do this. You could write it out in vector form and see that this is actually exactly a quadratic program just with no constraints. There is a quadratic term that ends up being positive definite, which you can prove is positive definite pretty quickly. But we can also show this just from our some basic rules too. So this term inside is affine in theta. The term x squared is a convex function, right? Its second derivative, that is a 1D function. Its second derivative is 1. So it's a convex function. And the sum of convex functions is convex. Therefore, this whole thing here is convex. Okay? So that's one way of showing it. You can also show the actual Hessian condition if you want to, but it really just follows immediately from the compositional rules of convex functions, how you combine them. The Weber point's also convex, and that one follows from the fact that norms are convex. So this here, this whole thing is just the L2 norm of xi minus z. This is convex in z, and therefore I'm adding up a bunch of those, and that's also convex in z. Done. That one we can't show again via the Hessian because it's not differentiable. So we really want to use the other properties there to show this is convex. Support vector machines. Those are convex. Well, we can show it a few ways, right? We could argue this is convex here because this term here is affine, therefore convex in theta. This term, one of these terms is affine. The other one is definitely, so this one term is affine. This other term, and therefore convex. This other term is just 0, so it's also a convex function. We know from our rules the max of two convex functions is convex. And we know the sum of convex functions is convex. And we know the sum of this function, so we know this whole sum of hinge losses is convex. And this term over here is convex. That's just the L2 norm of theta. Therefore, the whole thing is convex. So that's one way of showing it, right? You sort of go through these steps and say you keep sort of applying our rules that we learned about convex functions, and what you eventually get is you get the whole thing is convex. We can also, and effectively, actually, these are pretty much the same thing. What I basically did here when I defined new variables is I actually defined variables that correspond exactly to the max over these two things, effectively. So what I did here is also essentially introduce new variables, and now we can show that this is also convex jointly in theta and psi because all the constraints are linear constraints, right? These are all linear inequalities, and the objective is linear plus quadratic, and with quadratic, in fact, plus a 2 norm, which is convex. So I know I'm going through that very quickly. If you haven't seen it before, it could be kind of fast there, and really, you can hopefully see the basic idea that I'm doing here is I'm taking all these rules for convex functions, basically on these two slides. I think everything that I did there was on these two slides. And I'm just applying them to show that both all the constraints or the objective are convex. And thinking about it in this form, the G's are all convex, and the F is convex. So that's how you verify that a new problem, a new loss function you come up with is convex. I almost never actually derive the Hessian. It's usually a waste of time. It just takes some time, and you might make a mistake. I mean, I do sometimes, but I do it when I'm writing code, which I'll talk about in a second, not to verify something's convex or not. You can usually verify something's convex or not based upon just inspecting the problem. And you get kind of familiar with these things, and so you sort of learn the rules that make things convex or not. Okay. For example, you can also show that logistic regression was convex by that log sum exp formula. And all the other things we've seen so far actually can be proven they're convex just from a few rules like this, and just from a few sort of knowledge about what functions are convex. Okay, now let's talk very briefly about non-convex problems. And I'm going to be very brief here because I had nothing really interesting to say here. I'll tell you two things. First of all, non-convex problems are the case where either the objective, any one of these constraints, so either f or any one of g is non-convex. And again, subject to that fact that yes, if it's if it's non-convex outside the feasible region, then you can always just redefine it to be convex. So assuming you define things correctly here, if you define them correctly, if any one of these is non-convex, or if any of the h's is not affine, this is a non-convex problem. Any one of them does not hold to non-convex, and importantly, this means we do not have this very nice property we had before, saying that all local solutions are global. Now there could be local optima. That means if we're at a place that looks good right around us, who knows if we're actually optimal? We can't tell. And so, sort of as you might expect, then there are really two ways of solving non-convex problems, and two things we might mean when we say we're solving them. One of these says we're going to try to find a local solution. So if you have this function here, and we're fine with that point, that's okay, right? So locally it looks good. Maybe we just care about that. The other class of methods are global solutions, and that would say, well, now we actually want to find the true global optimum of this function. We really want to find this one here. And you can do that, but that takes a lot of time, typically. I mean, sometimes you can get lucky, but often that will take a really long time because you have to search essentially everywhere, right? Just because you're here, if you're here at local optima, you have no idea if there's other better points somewhere out there. And so you better come up with some sort of structure in your problem that lets you figure out where something like a condition on how smooth the function is, or some other restrictions on the total number of possible solutions. You need something like that in order to sort of know that you're going to find a global optima. So local methods, again, they're usually pretty simple. You just look for given some initial point. Say I initialize my x to be here. Local optimization says find me a nearby point that is a local optima, which is better than that first point. So this point here would be one that was fine defined. Importantly, this can be still really hard, actually. I mean, I'm describing it as being kind of easy, and you may have seen neural networks and say, okay, you just run gradient descent, it kind of works, okay. The problem, of course, is that it might be hard to even find a feasible solution, period. In which case you can't do it, right? It could be that even finding a feasible solution is hard. So you can't come up with an initial feasible point even. That satisfies all those constraints, because if the constraints are not convex, it can be hard to find a feasible point. So we kind of give up. This is actually why, for example, things like neural networks are nice, because every point is still feasible. So there's no constraints. So even if it's non-convex, you can still run gradient descent precisely because you don't have to worry about feasibility. The second category is these global methods. And these are things that really do try to find the optimal solution to a non-convex problem. They typically have worst-case exponential time complexity, with very few exceptions. There are a couple exceptions that you can solve non-convex problems globally, but there aren't that many. And I should also say, both these types of optimization are used incredibly often in practice. Right? Local optimization is used all the time in machine learning. Evidence being neural networks. Used everywhere. Same with global optimization. Used all the time. One of the more common global optimization problems for non-convex problems are called integer programs. Or one of the more common non-convex problems are called integer programs. Usually the way it's defined, that looks like an integer, a linear program, but you add the additional constraint that x has to be integer valued. This is now no longer convex, because the set of all integers is not a convex set, right? So 4 is in the set and 5 is in the set, but the average is not in the set, therefore it's not a convex set. I guess I answered this question right here. Why? But there are special algorithms. They're essentially based upon search techniques that can still solve it sometimes. And not only solve it, but guarantee that we've found the globally optimal solution without checking every possible answer. So that's kind of cool, because we can do it sometimes. But it still is, of course, worst case exponential time. All right, so now let me finish up. And I only have 20 minutes left, so I want to kind of go through this fast. But now I'm going to finish up now about, okay, I've defined all these problems. I've talked about convexity. How do we actually solve these things in practice? How do we find a solution to a convex problem? And the answer does vary. And it depends what you mean, also, when you ask this question. Do you mean, how does the computer do it internally? Or how should you go about doing it if you want to solve one of these? And these are different answers, by the way. How the computer does it internally is sometimes incredibly complex. But how you have to do it can be extremely easy. Sometimes. So first of all, let me answer the question, how does a computer do it? So again, we covered this a little bit when I covered machine learning, because I wanted to cover this same kind of point in the machine learning context. But essentially, for a convex function, we want to find a point for, if it was in 1D, we want to find a point where the derivative was equal to 0. The nice thing with convexity is that we know now that this point is not just a local. For general functions, if you find a point where the derivative is 0, it could be a maximum, could be a minimum, could be a local minimum, etc. For convex functions, any point where and let's assume we're talking about unconstrained problems now, any point where the derivative is equal to 0, that is guaranteed to be a local optimum. Therefore, it's also guaranteed to be a global optimum. So if we find this point, not only is this a flat part of the function, it is actually a global optimum. The same is true for for functions that are not differentiable. The same condition actually holds for what's called a subderivative or a subdifferential. Not subderivative, subdifferential. So great guarantee here. This is not just sort of a heuristic. This is actually the way we can find a global optimum. So how do we go about finding that point, right? This is all about finding points, or actually I'd have to say, of course, for the general case, we're talking about gradients here, or subgradients, not just a derivative, where the gradient, just like before, is defined as all these partial derivatives. This is the condition to find an optimal point of a convex function. Now, very important, this condition that we find a point where the gradient is 0, that is only an optimality condition for unconstrained optimization problems. When you add constraints, you are no longer required to have the gradient be equal to 0. That's actually very obvious because, let's see, how did I do this before? I'm just going to erase this and keep it simple. I don't think anything here is that important. Let's talk about a very simple problem. Optimize this function over this range. That's the optimal point. It does not have derivative equal to 0. So there are, of course, which I won't go into, there are analogous conditions for what implies optimality when you have constraints. But very importantly, this is only a condition, the gradient being equal to 0 is only a condition for unconstrained optimization. And essentially what it boils down to for the constrained case is that if you are at a point where the derivative is not equal to 0, it means you have to be actually at a constraint. Right? Because this is only the case because you are sort of, this constraint here, you are right up against. And so that was a very hand-wavy definition there. But essentially it boils down to, are you at a constraint or not? It's one of the constraints tight or not. And the sort of tightness actually gives you conditions on whether or not you need to have 0 gradient or not. So for the constraints that aren't tight, the corresponding sort of freedom in X may have to obey some zero gradient conditions. I was trying to define that there. Maybe I shouldn't have even mentioned that. I was trying to define sort of intuitively what some of these conditions were, but maybe it was just more confusing than it was helpful. Okay, so now let's talk about unconstrained optimization. So let's go back to the case of unconstrained, because a lot of times we are concerned in unconstrained optimization, or because this condition actually also holds for something like the sub-gradient, we can actually use this kind of condition for a lot of problems, like the SVM, if we think about it in terms of hinge loss. Again, with the caveat that this is actually not a gradient anymore, it's now a subgradient, and it's harder to find, et cetera, but let's not worry about it. I'll talk in a second about constrained problems, so you don't have to worry about these just yet. So, unconstrained problems. One thing we can do is find solutions directly, or try to find solutions directly. Okay, this is what we did with least squares, for example. Remember, I just wrote the gradient condition. It turned out we could solve that as a set of linear equations in our parameters and just get the solution. And we know now from convexity, this actually isn't just a flat point. This is actually the global solution. So if we can write down the gradient, and we can just solve for the x that makes that true, we are done. And the sad part here is this works for about one case, and it is quadratic functions. So functions like this. If you write the gradient of this, it ends up being actually this term here. Setting that equal to 0, you find that the best solution is this. So you can look at these notes again. It's great when you can do it, but quadratic functions are about the only case where you can do it. And in fact, least squares was a quadratic function. You can write least squares in that form, and that's actually why we were able to solve least squares like this, analytically. And again, for this to actually be a minimum, Q has to be positive semi-definite. I guess I should say positive semi-definite. It is the global minimum if Q is in fact positive definite, but just a minimum if Q is negative definite. Of course, if Q has 0 eigenvalues also, then this is kind of an odd thing because actually you can't invert it. For those that have seen this before, if I'm making no sense now, just ignore me for this little section here. But if Q is positive semi-definite and not positive definite, that means you can't invert it, it turns out, and so you have to actually use what's called a pseudo-inverse there instead, but everything else kind of goes through. Okay, so that's one way to find possibly a point with 0 gradient. Another way we covered also is gradient descent, right? Very intuitive here. The derivative, or the negative derivative of negative gradient points in the direction of sort of going downhill for a convex function. So all you do is you just take small steps in the direction of the gradient, negative gradient, right? So you take your value x, and we saw this before, so I won't dwell on it, but you take your value x, and you set it equal to x minus some small constant times the gradient. And that will, for smooth functions, for small enough alpha, this will actually get you exactly to the solution. For non-smooth functions, you have to do things like decrease your step size. Nando mentioned that a little bit, actually, sort of the intuitions there. But for things like the stochastic gradient, stuff like this, you actually have to decrease your step size as you go. But for the most part, this overall procedure here works. And it gets you, to an optimal solution where the gradient is in fact 0. And once it's 0, then you stop updating, of course, too, right? Because this is equal to 0 then, so you just stay where you are. One more method, which I'll only mention in passing. I don't think we have time, unfortunately, to get too into this. But another method is called Newton's method for finding a point where there is 0 gradient. And this will only actually apply to twice differentiable functions, to be able to compute the derivative, the gradient, and the Hessian here. But for functions like that, there's a method called Newton's method that actually will very quickly converge to numerical precision and find a solution that is, exact to the numerical precision of the computer. I unfortunately probably don't have too much time to go into this. essentially, this is if you've seen Newton's method for root finding. Newton's method for root finding says, given a function f, I want to find a point where f of x. I want to find x such that f of x equals 0, and you do it by repeating this iteration up here. You keep setting x equal to x minus f of x over f prime of x. That's for finding an x such that f of x equals 0 in the 1D case. Maybe I have time for this. So, okay, so if you have some function here, and you want to find a point where f of x equals 0, that's with a really bad function there. What Newton's method does is it basically forms this point, forms the line that passes through this point, and then picks your next function to be where that one intersects with the 0 axis. And then you evaluate here, form the derivative again, and then pretty quickly what you'll see is you converge to the point where this function crosses the 0 axis. And so you've found the root, what's called, of this function. The idea behind Newton's method for solving optimization problems is that we're going to use Newton's method, the root finding method, to find roots of the gradient. Right? We want to find a point where the gradient equals 0. And so you actually end up using a multivariate generalization of Newton's method that, after some derivation, ends up looking like this. You take x and you set x to be equal to x minus the Hessian inverse times the gradient. And sometimes you'll need to scale this, just like you do with gradient descent, but sometimes you don't need to do that actually also. Sometimes this just works fine. And that will, if you repeat that iteration, you will actually also get to a point, assuming, you might have to do things like use step sizes, but assuming you do all that, you will get to a point where the gradient is 0. And what's very nice here is that this iteration will converge to numerical precision incredibly quickly. Again, when you can do it. So this is how you get, the function has to be twice differentiable. All these other things have to sort of hold here. But if you are in that situation, this will converge incredibly quickly. You need something like log of 1 over epsilon. So if you want to converge to epsilon accuracy, you need log epsilon iterations. Once you're in a certain region, I should say. And log is really small, right? It's like 6 for any reasonable precision that you have. I mean, for really any number, you should approximately think of, for most things, maybe the things we're talking about here are a little different, but, log of some quantity is like 50 at most for anything you actually see in the real world. And so log is really small. But the caveat, of course, is that each iteration here is much more expensive. So each iteration, this Hessian is an n by n matrix. So to compute a single iteration of Newton's method, you have to invert an n by n matrix. That naively is cost n cubed. And so we're certainly not talking about something you can do with trillion parameters. Unless you really exploit structure a lot, which, by the way, is what a lot of sort of additions to gradient descent do, is they sort of get us closer towards Newton's method. Okay, let me just very briefly talk about constrained optimization here. Unfortunately, I have to be a little brief because I've been talking so far about the unconstrained case where we have no constraints, right? In the constrained case, there are, now we don't have this condition anymore that it has to be 0. There are other conditions you can do, and actually a lot of methods try to directly solve these other generalized conditions, but there are a couple of simple things you can do too. One of the simplest algorithms is called projected gradient. And so what that is that's exactly like gradient descent. So what that is that it's just like gradient descent, except after your gradient step, you follow it by a projection operator. Where what the projection does, the projection finds the closest point to where you are currently in the feasible region. So now, it is not always the case that it's easy to come up with a projection. But if, say, your constraint set was that x has to be greater than or equal to 0, well, this one's very easy to project onto. The projection is you take every coordinate, and if it's less than 0, you set it equal to 0. So there are problems for which you can do this projection very efficiently. And in that case, this generalization of gradient descent ends up working quite well. And something very similar to this is actually kind of at the root of a lot of optimization methods in machine learning. You can also project them onto other things as well. But that's a simple one. And then finally, let me at least highlight one thing that's a little bit more complex than that. And this, by the way, is, well, not quite this, but something very similar. This is how a lot of sort of off-the-shelf libraries that you use for optimization actually work under the hood. One idea, is that you can actually transform constrained problems that are smooth, because you can actually write them usually as with every term being differentiable. You know, you take all the non-differentiable things and move them to the constraints. You can actually write constrained problems as unconstrained problems, where you replace all the constraints. Rather than having constraints, you use this function here called a log barrier. And the idea here is this log term. So this log term, right, if I take the log of negative something, that kind of looks like this. As you get closer to 0, rather, as the constraint gets closer to 0, it'll get steeper and steeper. And so essentially, because it's the negative log, I should also say. And you know, g of x has to be less than or equal to 0, but if this is the log function. So I should probably write it like this, actually. So this is g of x. G of x. And as it goes closer to 0, the log, of course, gets closer and closer to infinity. The negative log gets closer and closer to infinity. And importantly, we have some scaling parameter t here, where as t goes to 0, this problem approaches the original constrained problem, right? Because as t goes to 0, that term on the left, or sorry, the right, your right, term on the right here, it has no influence in the problem because the weight's very small. T is very small unless that term is actually positive, and then it's infinite. All right, so you'll sort of, as t goes to 0, you have this log term kind of approaching this switching function, and that lets you therefore capture any constrained problem as an unconstrained problem. That's very cool. Now, the caveat, of course, is that yes, this is an unconstrained problem, but it is a really hard problem to solve because numerically, it's what's called very poorly conditioned. Essentially, you have this scenario where very, very small changes in x create huge changes in your objective value, which make it very hard for numerical solvers to actually figure out a solution to this on a computer. But what's really, really interesting here, and this took a long, long time to prove, by the way, that you can actually do this. So this is not obvious that this works at all. But what you can show is that by very carefully scheduling how you update that t parameter, you can find a set of problems that are all solvable on a computer, that are all conditioned well enough to be solvable, and which converge to the global solution of the constrained problem to numerical accuracy. And so actually internally, this is almost how a lot of actual solvers work. So if you've heard of any sort of convex optimization problem solvers, things like Nando mentioned, like Cplex, for certain problems, this is actually how they solve it. Or something very similar to this. Okay, and so let me then just conclude with one more thing. I took you through quite a set of things you can do. Gradient descent, Newton's method, this crazy log barrier stuff that has all sorts of sort of weird conditions. You have to schedule this thing, right? That sounds pretty complex, and it is pretty complex. So the thing that I want to sort of impress on you also is that if you have to solve a problem like this, do not try to write one of those things. These things have already been written. They already exist. Just use an existing library. And in particular, in the last, say, 10 years, a bunch of libraries have come out. These are things like, well, actually, it's longer than 10 years because the OR people had this way much before we did it in computer science. But things like CVX, YALMIP, or a newer one, CVXPy for Python, these libraries let you write convex problems almost as you just want to write them originally. So almost like the max of this and this, and that just does all the work for you, forms them into the proper form, solves them with some existing library, etc. So you can actually type in problems almost exactly as you want to write them into a language like Python or MATLAB, and just solve them. And this is a pretty new technology. I mean, these things like ample and gams have actually been around for a while, but a lot of this has just sort of become up in the last 10 years, say. So let me just show you, this is my last slide. Let me just show you one example of this. This is a solution to the Weber point problem. In fact, even a constrained Weber point problem in Python. And the actual code here is 2 lines of code to find the Weber point. I'm using a library here called cvxpy. And essentially what you do is you say the function here is equal to the sum of a bunch of norms. The norm of z minus x. For all the x's in this range, and that's actually it. That's the code, and then you just solve this subject to the constraint that these have to sum to 0. So you can play around with this. You can just Google cvxpy or cvx or any of the other ones, and you'll find them. The idea here is that there's actually a lot of work happening behind the scenes to transform this into, first of all, a constrained problem. A smooth constrained problem, and second of all, one that can go into a standard form solver that be solved by a interior point barrier method, they're called, or interior point primal dual method. It's an even fancier one. There's a ton of stuff going on behind the scenes here that you don't have to worry about. You just write minimize what I want to minimize, subject to the constraints I want to impose, and it solves it. Again, don't try to do this for problems like you deal with, like other people have been mentioning here, where you have 1,000, not 1,000 is fine, where you have a trillion size variable z. That will not work. It will just stall out, take forever. But for problems at a reasonable size, you can find an exact solution, exact numerical precision by doing this. Okay, so I'm a few minutes over, so maybe I'll defer questions on this last bit to being offline. But thank you all. Stop the video.